So, hello everyone. I'm Shalabh, a postdoc at the Astro Group at ICTS, and I'm going to present before you some of my ongoing work on spherical Einstein field equations and hyperbolic slices. So, I thank the organizers for letting me present my work here, and I have been doing this work in collaboration with my friends. Ines and Christian are the PhD students. Miguel, Alex, and Edgar are postdocs, and David is the faculty. All of them are in Lisbon, and Ines is in Valencia. And who knows, if people at ICTS are not fed up of me, we will see more names from ICTS in the near future. So, so by spherical Einstein field equations, I simply mean Einstein field equations in spherical symmetry. And as we go along, I will introduce the hyperbolic slices. So as the broad area of my research is numerical relativity, so I should motivate, first of all, why do we need numerical relativity, or NR in short? It is simply because Einstein field equations are a system of coupled partial nonlinear differential equations, and because of which we still don't know how to solve them analytically for a general setting. And the ultimate motive of NR is evolving any initial data or initial boundary data as well if we have an outer boundary as well. So any initial data which evolves, which also includes any initial matter distribution to any desired degree of accuracy, and extract the resulting gravitational wave signal at sky plus, which is the future null infinity. So first of all, what is sky plus or the future null infinity? It is simply the infinite future of all future directed null rays or null trajectories. In simple words, I'm standing here, I'm pointing my laser pulse in any direction. So this laser pulse will reach the future null infinity in the infinite future. So this is the simple definition. And in Minkowski spacetime, we can visualize this easily. For example, if we write the metric in spherical polar coordinates, big R is my radial coordinate, and sigma d sigma square is the metric on a unit sphere. We can introduce outgoing and ingoing null coordinates denoted by v and u, and in terms of these coordinates, this is how my metric looks like. We can see that, of course, since the time coordinate can take any real value and big R is positive semi-definite, my u and v coordinates take values from minus infinity to plus infinity, and as the definition suggests, v is always greater than or equal to u. So in terms of these coordinates, we can easily define our regions of interest, like as the time coordinate goes to infinity at a constant radial coordinate, we reach the future time like infinity, which we denote by small I plus. And similarly, as t goes to minus infinity at a constant radial coordinate, we reach small I minus. Similarly, as we reach as we reach R going to infinity on a constant time slice, we reach space like infinity. And when we take v goes to infinity at a constant u, we reach the future null infinity. And as u goes to minus infinity at a constant v, we reach past null infinity. So the question comes, why are we interested in sky plus, a future null infinity? The reason is simple, because this is the only region where we can define the gravitational waves unambiguously. So there's no other reason. And now, since all these regions of interest involve infinite values, the question comes, how do we map them on a finite computational grid? Why a finite computational grid? Because we have only finite resources to do any simulation. So the answer is using compactified coordinates. So here's an example. If we introduce compactified null coordinates denoted by small u and small v, which are defined like this, arctan of big U and arctan of v respectively, this is how our metric looks like. And small u and small v takes value from minus pi by 2 to plus pi by 2. So we can see that so all these all the coordinates in this metric have a finite domain, but problem is that as u or v goes to pi by 2 or minus pi by 2, this factor blows up. So to regularize this metric, we introduce another metric, which we call the conformal metric, denoted by d small s square, which we define as omega square times big S square, and omega is given by this. And this is how my d small, our conformal metric looks like. So, and which is regular everywhere. So in terms of these compactified coordinates, this is how my Minkowski spacetime looks like. So I plus and I minus are my future and past time-like infinities. I0 is my space-like infinity. Scribe plus and scribe minus are my future and past null infinities. So the vertical line here is the origin. All these solid curves are the level sets of the constant time slices, and these dashed curves are the level sets of radial coordinate or the constant radius curves. And you can see all these, okay, and these solid curves are an example of Cauchy slices. So these are the slices which meet the space-like infinity. So now let's come to the original problem of mapping sky plus on a computational grid. How to solve it? So this problem needs to be tackled at all three levels: geometrically, analytically, and numerically. In the geometrical front, we need to introduce a slicing which facilitate mapping sky plus on a computational grid. By analytical front, I mean we need to define a well-posed formulation of Einstein field equations. So what does well-posedness mean? An initial value problem or initial boundary value problem is called well-posed if there is a solution, if there exists a solution which depends uniquely and continuously on the initial data and on the boundary data also in case of initial boundary value problems. And in the numerical front, we need to derive a discretization scheme which preserves this well-posed formulation of Einstein field equations even at the discrete level. But the problem is that none of the existing methods of calculating the gravitational wave signal satisfy all these three criteria. So here's an example, like we can see all these Cauchy slices, they terminate at space-like infinity, not at null infinity. So these slices are useless when we want to map sky plus on a computational grid. To do that, we introduce another kind of foliation, which we call hyperboloidal slices. So these slices are space-like everywhere, but they meet sky plus rather than I0. So by introducing such foliation, we solve the problem at the geometric front. So analytically, we write the Einstein field equations in terms of generalized harmonic gauge. So first of all, the choice of gauge simply means the choice of coordinates. We just choose a set of coordinates and write the Einstein field equations, and these coordinates satisfy some properties which we call the generalized harmonic gauge. And why are we interested in this gauge? Because the Einstein field equations have been proved to be well posed in this gauge by various authors. And in the numerical front, we derive a scheme, a summation by part scheme, which proves stability for a class of linear wave equations on these slices, and actually for a broader class of slices. But why are we interested in linear wave equations? Simply because the principal part of Einstein field equations in generalized harmonic gauge mimics the wave operator for the linear wave equation. By principal part, I simply mean the part of the equations which contains highest derivative. And these are some of the numerical results. So x-axis is my compactified radial coordinate, which goes from 0 to 1 as we go from the origin to scribe plus. So this is the radial coordinate defined on these slices. And the y-axis simply gives some amplitude of various dynamical variables, which are our metric components here. So in this animation, what do? We just pump some data from the initial boundary, from the inner boundary, and we see how it evolves with time and leaks through scribe plus. So good news is that we don't have any noise coming from scribe plus, which is good because physically we understand that no information can come from scribe plus to us. So whatever we pump inside should leak through scribe plus completely in a finite time, finite hyperbolic time. So in summary, numerical relativity is presently an indispensable component of gravitational astronomy, and accurate predictions of gravitational wave signals involves including scribe plus on a computational domain, computational grid. And we just saw that how hyperboloidal slices facilitate us achieving this goal, and we gave a prescription to define our Einstein field equations on this slice which give some promising results. So this is the work in progress, and stay tuned for more results. Thank you for your attention. Any question or comment?
Thank you, Shalabh. So our next speaker is. Sorry.
Bye. You are fed up
Hello.
so easily.
Yeah, hi. So here, I've got
Hi.
a question. Just now you said something about noise coming out of Sky Plus. What does that mean? Why would you see noise?
Okay, so basically we are evolving it numerically, and Sky Plus basically is a point where we are mapping an infinite coordinate on a finite at a finite distance. So it is a very sensitive point, even especially when we evolve something numerically, and any sensitive point is prone to generate numerical noise. So this is a consequence of our numerical scheme, which guarantees that no numerical noise can be generated at Sky Plus, which also means that as we increase resolution, our signal, our result will converge to the continuum limit. So which also guarantees accuracy of our waveforms.
If there was noise coming out of Sky Plus, how would you see this on this
So
animation?
we could see some signal coming from inside, like some reflection. So there is no reflection coming from Sky Plus to the bulk, right? So some pulse would hit inside from Sky Plus. It could be noisy also, some noisy pulse also.
Sky Plus in this? Like,
Okay, one,
coordinate
small r
area.
equals 1. So it is like small r goes from 0 to 1 as we go from origin to Sky Plus. So compactified radial coordinate, hyperboloidal radial coordinate.
Okay, thanks.
Could you go back to the graph that you have? Yeah. What are these 3 lines exactly? I'm not sure
So
what's
some
happening.
metric variables. You don't need to know exactly which metric variables.
But they characterize the GW wave?
In spherical symmetry, we don't have gravitational waves. So
Okay.
these are the results only in spherical symmetry. And thing is, all our variables are dynamical. Okay, strictly speaking, by Birkhoff's theorem, we don't have any dynamics in spherical symmetry if we have vacuum. But if we have matter in spherical symmetry, all this signal can be physical because we can have collapse or dispersion, etc. But again, there will be no gravitational waves.
So is this some arbitrary initial condition?
Okay, let
that
me
you
show
put?
you. So in spherical symmetry, in spherical polar coordinate, this is the general form of the metric, where all these variables are dynamical variables.
Yeah.
So,
So these
are
are
some
the
of these
variables
variables.
that you plotted?
Yeah, so these are some of these variables as function. Actually, not exactly this, but we rewrite our metric like this, where C plus and C minus are outgoing and ingoing light speeds. Delta and is another dynamical variable, and R circ is my aerial radius. All of them are dynamical variables. Okay. Any other question or comment? Yeah, please.
Metric, right?
No, not really.
That's-
I just
so
demonstrated how we can achieve compactification. In our compactification, we don't use conformal compactification. So what we do is that we define another time coordinate, which we call hyperboloidal time coordinates, and define, so all these slices are the level sets of that time coordinate. And so time coordinate is not compactified at all. But on these slices, we introduce a compactified radial coordinate. That's it. So in conformal compactification, all my T and R coordinates are compactified. In this case, our T is not compactified, but R is compactified.
Okay. But what was the purpose of the rescaling of the metric that you did? I mean,
Rescaling.
yeah, you rescaled metric by this omega factor, right?
Oh, okay. No. So again, I was just demonstrating conformal compactification. And our compactification is not conformal, it's a bit different. What I simply meant is how we can regularize all the components of the metric. This was my motivation, nothing else.
Okay. But in a numerical evolution, you will not use this metric, right?
No,
This,
no, no.
The original, you have to use the original metric.
Yeah, so the one which I showed. So this is the general metric in spherical symmetry, in spherical polar coordinates, but we use these variables.
Okay. Okay. Thank you.
And of course, since all these, all the dynamical properties of these variables will follow at least like 1 by r. So we need to rescale all these 1 by r behavior so that they are of order 1 everywhere. So here rescaling comes. Any other question or comment?
Actually,
Okay,
over
we're running
time.
out of time. Sorry, not my fault.
Thank you, Shalabh, again.